So 9-6 counting principles, we're going to be learning how to count the number of events in a sample space when it's too expansive just to count them. We're going to start with basic ones though, with selecting a pair of numbers at random. So 8 pieces of paper are numbered 1 through 8 and placed in a box. 1 piece of paper is drawn from the box. Its number is written down, and the paper is replaced. When you read these, replacement and non-replacement are really important, okay? Because if I don't replace it, can I get that number again? No. I'm going to pause. Okay, so replacement's important to know because then you have a second chance to do it. A second piece of paper is drawn from the box. The number is written down. How many different ways can I get the sum of 12? So I have numbers 1 through 8, and I have 2. I'm taking 2 numbers, 8 and 4.
6 and 6.
What about if I drew 4 first? Yeah? Okay. 6 and 6 you can't distinguish between, right?
You put the other 6 first.
That you can't distinguish between them. Okay? Actually, yeah, we got, what? 5 and 7. Any others?
No.
Okay, so how many ways can this happen then? 5. So that wasn't bad, right? That wasn't bad to figure out. When they're that easy, that's what you'll do. When they're not that easy, you'll do something else. Okay, this counting problem can be described by saying that the random selection occurs with replacement. If you would happen to do it without replacement, how would that change it? Because we had 5 with replacement.
What is replacement?
Like you put the number back in the box.
Oh.
So if I took out a 5, then I have a 7. Right?
Oh, and then you went from 6 and 6.
Where'd you get the 7?
Out of the box. 1 through 8.
That's
The
last problem.
It's the last problem.
Oh.
Okay.
And then you would just.
So, but I could get 7 and 5 still, yes? But could I ever get 6 and 6?
No.
No, because I pulled out the 6 and it's sitting on the side, so I can't pull out a 6 again, right? Can I get 8 and 4 and 4 and 8?
Yeah.
Yes. So it went from 5 to 4. So in general, without replacement, the number of the ways it's going to happen be less. Yeah. Okay. So when you're reading a problem, make sure you know that if it is replacement or non-replacement. Okay. The fundamental counting principle is you multiply the number of ways an event can occur. It can extend as far as you need it. So, yeah.
When you write that down?
Well,
Okay.
we have the example on the next slide. You could put that as an example of it.
I'm gonna write the bold now.
So if you just want the definition, it's just to multiply the number of ways an event can occur.
My back hurts, Miss Mick.
Womp womp.
Sorry.
I just didn't say that. My back hurts, and I'm not complaining. Hey, but if you ever tell every day is a stretch.
You guys ready?
Every day is a stretch. I mean, not anymore. Last
Okay.
semester it was, but now we got Kanye, so we're gonna eat that.
How many different pairs of letters from the English alphabet are possible?
Huh?
How many different pairs of the English alphabet are possible?
48.
Okay, so how many letters are in the English alphabet?
24.
26.
I thought it was 24.
I don't know.
26.
It's like,
Pretty
Wah,
sure there's
wah.
26. Okay, so if I pick one number at random, there's how many different choices?
Well, it's 26.
26, right? But if I've picked one, how many choices do I have now?
25.
25. So I would take 25 times 26. Multiply. Do it.
Um, 658.
658. You guys agree?
Wait. No, 650. Sorry. My two zeros like merged together. It's okay.
Okay, so how many different pairs are there? 650. Okay?
What's the 25 come from?
Because I picked one number. Like,
Letter.
because it says, letter. Because it says different. So that means it can't be raised with replacement. So if I just asked you how many pairs without saying different, could I just take 26 squared?
Yeah.
Yes. Which would be... So if it was just pairs and not different pairs, it'd be 676. Okay, so this is different pairs. And this is just pairs. So they aren't always going to say with replacement or without replacement, but the words they tell you in the problem are going to distinguish that. So I will tell you when I do these problems, I tend to have to read them at least twice to make sure I'm not missing anything. I usually read it once, set it up, read it again, and make sure I set it up correctly.
Probability.
Lots of reading. Okay, telephone number in the United States currently have 10 digits. The first 3 are the area code. The next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with a 0 or a 1. Okay, so 402, because it said in the same area code, right? And then we have 3 digits, and then how many more? 4. Okay, so I need to know how many different. Well, in a telephone number, how many digits can you choose from? 0 to what?
9.
0 to 9. How many digits is that?
9,
10, because you have 0. Okay, so there's 10. How many choices do I have for the first number? 8. Why 8?
Because it can't begin with 0 and 1.
It can't begin with 0 or 1. How many choices do I have for the next number?
10,
For the next?
10,
For the next?
10,
For the next?
10,
Next?
10,
Next?
10.
And what am I going to do with all these?
Multiply.
So I got 8 with how many zeros?
6.
It's a lot.
Or 1 area.
So why did they have to add, if it's 8 million, why did they have to add more area codes to Lincoln?
More.
There's not 8 million people in Lincoln. Or there's not 8 million households in Lincoln either.
Because there's.
How many telephones are in your house? How many telephone numbers are in your house?
Telephone numbers or cell phone numbers?
That is a telephone number.
Is it? Okay,
Yes.
Like, I'm thinking like the
No, but telephone numbers. How many telephone numbers occupy your home space?
3.
3?
There's a lot of extra numbers.
Oh, 4, sorry.
4? Okay.
And in
I got like
total, I have like 10.
6.
I
6. Okay, when I grew up, we had one phone, and then we were all excited when we got our own line for us kids. So we had 2 numbers for our whole house. Now my household has 5 people, and we have 6 phone numbers because, well, we used to have a house phone. We don't anymore. So why are we running out of telephone numbers? Because we're not doing homes, we're doing what? People. And some people have a work phone and a personal phone. So that makes a difference, doesn't it? Okay. So could I change this problem? How else could I write this problem? Could I put like numbers not repeating?
Yeah.
Okay. So if I did numbers not repeating, the first one would be 8 still, because it's 0, 1, right? What would the second number be? 9. What would the next number be? 8. Yep. And next?
7.
Next?
6.
Next?
5.
Next?
4.
So you'd have to take 8 times 9 times 7, 8 times 9 times 8 times 7 times 6 times 5 times 4. What do we got? 20, right? 120. 840. Oh, I'm done. I can get there. 64 times 9 times 840. Look what it does. What did it do?
Cut it in half. Almost.
Yeah, I mean, it's a little over half, but that made a huge difference, didn't it?
That is not over half.
That's not even close.
That's 483.
That's half.
Oh, no, that's not even half. Sorry, that's like,
$500,000.
I was doing 800,000. I was with you there, Emma.
Yeah. I thought it was 8 million. So 8.
Because 16th, almost the 17th. So when I add restrictions on it, is it going to limit the possibilities? Because I could say it couldn't end in a 0 or a 5. And then would that change my ending number options? Yes. So we just got to read careful. Okay, a permutation. Determining the number of ways that n elements can be arranged in order, an important application of fundamental counting principles. Permutations. An ordering of n elements. One element is first, one element is second, one element is third. Order matters. I don't have my order matters. Okay? In what things do order matter?
Subtraction.
Well, yeah, but that's not what I was talking about. How about, okay, does it matter how many, like if I say, how many ways can I make 2 groups of 3 in this room? Would the order matter of the 3 people? No. But does it matter if I say, how many groups of 3 can I make in this room with one being the president, one being the vice president, and one being the secretary? Does order matter then?
Yeah.
Yes, because with those 3 people, I could have 3 different groups, couldn't I? Does it matter when I say how many people can I put in a group for a race? No. But does it matter when I say how can I place them in the race?
Yeah.
Yes. Batting order, does it matter the order?
To some coaches.
No. Batting order doesn't matter the order. Can I just go up to bat any way I want? No. You have a what? Order. Okay? So when you read the problem, if order matters, you're going to use a permutation. Okay? And we will get a formula for that for when we do not place everything. Okay? But permutation to start with, we're going to use this fun thing. What is that? What's that exclamation point? Just remember? Factorial?
Yeah.
Okay, so it's really excited because it gets really big really fast, right? So with the telephone numbers, when we did that after we placed the first one, we did 9, 8, 7, 6, 5, 4, right? So if I have 5 people and I need to know how many different ways I can place those 5 people in a row, it would be 5 times 4 times 3 times 2 times 1. So 20 times 6 would be 120 different ways I could place them. Make sense? Tell me when you're okay. Am I okay? Okay, so how many permutations are possible for the letters A, B, C, D, E, F? How many letters do I got? 6. So it's going to be 6 factorial. So that's going to be 6 times 5 times 4 times 3 times 2 times 1. Hopefully you remembered that 5 factorial is what? Just did it. 120. 720. 5 factorial is a good one to remember. Because then you can go up or down. To get to 4, it's pretty easy. You got 6, 24. Right? 1 factorial would be 1, 2 factorial would be 2, 3 factorial would be 6, 4 factorial would be 24. Not 24. Yeah, 24.
Why do you think it times 120?
Because 5 times 4 times 3 times 2 times 1 is 120.
Oh, you just took the 6.
Uh-huh. So if you can remember portions of it, it makes it easier. Okay, remember that for permutation, order is important. So the A, B, C, and B, A, D are different. Okay? But if order doesn't matter, they're not different. Does that make sense, what I'm trying to say? Come. Tell me when you're good, Alex. Okay, 8 horses are running a race. How many different ways can the horses come in first, second, and third? Assume there's no ties. So all I need is first, second, and third. I'm not placing all 8. Only how many? 3. So how many choices do I have to come first? 8. How many choices do I have second?
7.
Third?
6.
6. So you want to do 42 times 8? Yeah, probably. That's easier, right? So 6, 32, 33. So 336 different ways that they can place first, second, and third. Did I multiply that right? 16, carry 1, 32, 1, 33.
Yeah.
Okay, so I'm not oblivious. I know that you are going to use a calculator, but you do need to write down your work. Got me? I would try to be doing some of this and just keep using your mental math like we do and check it. Because if we don't use it, we lose it. But this is an appropriate section to use your calculator. Especially when we were multiplying, 8 times 9 times 8 times 7 times, I did what I could and then I'm like, okay, calculator. Okay. If you want to choose and order our elements of a collection of n, so not all of them, okay? If I would have asked you to place all 8, you would have done 8 factorial, right? 8 times 7 times 6 times 5. But we placed 3. So we did 8 times 7 times 6. That was easy, okay? But they're not all that easy. So we have a formula for this, okay? It's a permutation. What do we need to remember at permutation? What matters? Order. So it is NPR. N is the total number there are. R is how many you want. N is all. Got it? N will always be bigger. It is n factorial over n minus r factorial. Does that kind of look familiar?
What's R?
R is the number of things you want to pick. N is the number of things that there are. N is what you want to pick. Does this formula look familiar?
Yeah.
What's it kind of look like?
One we used the other day.
The one you used the other day, which was choose R, and it was N factorial over N minus R times R. Okay, you are going to use both. Permutation matters, combination does not. Okay, which one's going to have a bigger answer? Permutation or combination? Look at the denominators. Which one's going to have a bigger denominator? Combination. So if my denominator's bigger, I'm dividing by a bigger number, I'm going to end with a smaller number. So which one's going to have a bigger answer? Permutation. Remember I said how many groups of 3 can I make in here? That's going to be a lot less than how many groups of a president, vice president, and secretary. Because it makes one group into 3 groups. Make sense? Okay, so we're going to do the horse race again, but we're going to use the formula. So I don't remember what our answer was. What was our answer?
What? 336.
Okay. 336. So we better get the same answer, right? So we're going to use first, second, third matters, right? So we're 8, permutate 3, because 8 is what we started with, 3 is what we want. So what goes in the numerator? What goes in the
Numerator?
no, 8 factorial. What goes in the denominator? 8 minus 3 factorial. Oops. So yes, it is 5 factorial. So now we're going to reduce that. And remember, we're not going to write it all out. We're going to write 8 times 7 times 6 times 5 factorial. Why did I stop at 5 factorial?
Cancel it out.
Because I can reduce it out. And 8 times 7 times 6, unless we did it wrong the last time, is still 336. So even the way we did it, we were still doing the formula without knowing we were doing the formula. Now, there are times you are definitely going to use the formula. You're not going to write 8 times 7 times 6. And there's going to be times you're just going to write 8 times 7 times 6. Okay? If I have 85, choose 15, are you going to write all that out? No, you're going to do the formula. Okay, distinguishable. Distinguishable means I can tell them apart. Do not write that formula because it's going to confuse you. Write the word and then write distinguishable permutations, and then you're going to put this example, and then you can write on the example. Okay? So a distinguishable permutation means non-repetitive. That would be distinguishable, correct? So if I have the word banana, it says how many distinguishable ways can the letters in banana be written? So N is the number of things we have, yes?
Mm-hmm.
So how many letters are in banana?
6.
6. Okay? So we take and do 6 factorial. Then we go underneath and every letter. How many B's are in banana? 1. So 1 factorial. Times. How many A's are in banana?
3.
So 3 factorial.
And then 2.
And how many N's are in banana?
2.
2. So when you are done, your 1 plus 2 plus 3 should add up to 6. Because there's 6 letters. Does that make sense? Your bottom should add up to what your top factorial is. And then you do the math. So 6, I'm going to write 6, 5, 4, and I'm going to stop at 3 factorial. Why am I stopping at 3 factorial?
Because
Is that the biggest factorial on the bottom?
Yeah.
Yeah. So I have 3 factorial, and then 2 factorial is basically just 2, correct? Because it's 2 times what? 1. And 1 factorial is 1, so I'm not going to write those. So I can reduce the 3 factorials, and I'm going to reduce the 4. How about you?
And the 2?
Uh-huh. So 30 times 2 is? $60. So how many distinguishable ways could I order the letters in banana? 60. Okay. How many ways could I order the letters in banana would be 6 factorial, which is 720. So if there's 720 different ways to write those 6 letters, but only 60 distinguishable ones, that means there's 60 ones that look the same. Does that make sense?
Yeah.
Yes, sir.
Can you only reduce the 2 to 1 number up there?
Yes, because once you reduce it once, it's gone. That's a big difference, isn't it? Now, this is used on things that are repetitive. Think of some words that have a lot of the same number letters in them. Mississippi. I think that's my next example. Words are weird. Oh gosh, don't. Okay, words are weird because there aren't a lot of words that have a lot of repetitive letters. But I think in your assignment, they just give you a random bunch of letters and say how many different distinguishable ways. I don't know if they do words.
What about like Hannah?
What?
Like Hannah, if it's all 2s.
Yep. But how many letters are in Hannah?
6. H-A-N-N-A.
Okay, so it's 6 factorial, and then it's 2 factorial, 2 factorial, 2 factorial, right?
6 over 6?
So, well, you go 6, 5, 4, 3, 2, and then you have 2, 2, and 2. So 2 reduces, yes? 4 reduces. So 30 times 3 is 90.
Okay.
Why'd you reduce the 2 2s into 1?
Because 2 times 2 is 4.
It takes out the whole 4.
Oh,
You
okay.
guys both just like yelled at me. I didn't know there was Miss
This Smith likes to yell at
We
people.
spoke-
I wasn't yelling, I don't think. 2 times 2 is 4. So it's easier to take it out of one thing than take it out of the 4 and the 6 and then have to multiply.
I knowingly I would do
Yeah, you probably would. That's okay.
2s are just easy.
that. I don't think that.
Okay. I think, I don't have. Okay, so combinations. Combinations, a method of selecting subsets of a larger set in which order does not matter. When does order matter? What do we use? What's the thing we use when order matters? Permutations. What do we use when order does not matter?
Choose.
Combinations.
Oh, wait, yeah.
Or choose. Combinations.
I like saying choose.
I usually say choose to, but it's combinations. For instance, the combination of ABC and BAC, if order doesn't matter, aren't those the same groups?
Yes.
Yes. So there will be less combinations than permutations. Always.
Okay.
We got here.
No.
Isn't combinations what we did like 2 days ago?
Mm-hmm. You did it with the Pascal's you can use Pascal's triangle to calculate them.
Oh, yeah.
Yep, it's the formula. The combination formula is the formula for the choose. Okay, are you good? Okay, so how many different ways can the 3 letters be chosen from A, B, C, D, E? The order is not important. So we have A, B, C. We're going to write them out. And then you're going to say we need to use the formula. Then what?
CBA.
Nope. CBA is the same.
This is
So then C, D, E.
Okay. Can I want to do something real quick. We did these three, so then I would go to these three, not skip around. Does that make sense? When you do this, you want to do some sort of order in it because you'll skip things.
Can you do like A, B, D? Like,
Yeah. But we'll go. Let's just go down the. Let's go down the line first. So A, B, C, B, C, D, C, D, E, and then you could go D, E, wrap around to A, and then E, A, B.
E,
Okay, so now we're done just like going in order. Now we got to skip, right?
So then A, B, D.
A, B, D. Is that one?
A, B, E.
A.
That's A, B.
We got that one right here.
But you did A, B, B.
Oh, I meant D. I meant D. Sorry. I think she was saying B when I was writing D and I wrote B. Okay, A. Can we do A, C, E?
A, C, D.
Head up, Alex. What?
A, C, D.
A, C,
That's,
D. Yep.
there's B, C.
I was just checking. I think we have all the A's.
D. Do we have A?
Do we have all the B's?
No.
B, C, D. Do we have B, D, E? No.
No.
B, D, E? B, E, A? Yes.
Yeah, maybe have
I normally do. I should have written them like this. So I'll write like all the A's together. Does that make sense? Like all the ones that start with A.
it all has.
And then I'll go next to it and write all the ones that start with B. This is what I do. Because should they get less, like as I go across, yeah. And then C, D, and then I have the one E. Okay, is that it?
I don't think so. I think so.
So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9 ways. Okay. Let's do the formula. Do you guys remember again? N, choose R. So it was N factorial over N minus R factorial, R factorial.
Yeah.
Okay, so what's my N?
9.
No, what's my N?
5.
5. How many am I choosing?
3.
3. So 5 factorial over 2 factorial, 3 factorial. How'd I get 2 factorial?
You took 5 minus 3.
Okay. So I have 5, 4, 3 factorial. And 2 times 3 factorial.
You can reduce that.
So that reduces.
So it's just 5.
It's
Or
10. So we're missing 1.
It's okay. We don't
Okay.
have to do that.
Which one's easier to do?
The NCR.
Yeah. When I took my when I took my probability class, I would be like writing them all down, and my instructor would get so mad at me. He goes, "You know how many there are? Why are you writing them down?" I'm like, "I don't know. I think it was like the puzzle part of it." And he's like, "You were spending you're like wasting your time." So if I was on my own, I would probably go until I found the 10th one because it would bug me that they don't
B,
match.
C, E.
B, C, E. B, C, E. Yep. But you notice how it went. I had 4, I had 3,
Only 1.
and then I had 1.
1.
And 1. So they'll go down.
Well,
What?
E, A, B could go with the A if you put the A first.
You're right. You could, yeah. If you really want to go with A first, your A could be really long, and the rest, you might not even have any E's. You know, E's or D's. So. Okay, like C is this one would have to be C. This could be here, right?
DDA could be just A.
And this could be here. So yeah. So if you did all your A's would be 6. And then you'd have 3, and then you'd have 1. Okay, just did it. We don't need to do that. That's the same example. Do you have this written down on your paper?
Yeah. NCR?
Yes. Do you have NCR written down?
No, but I will put it down.
Okay, because as soon as I quit touching it, it's going to go away because I didn't turn my pencil. Okay, you might want to write it on today's. I don't know. Okay, when do I know to use a permutation? When the order matters. When do I use combination? When the order does not matter. Is it going to come out and tell me order matters all the time? Nope, you're going to have to read the room. Good? Kyan, you good?
How many slides do we left?
I don't know how many slides we have left. And we only have 2 minutes because I shut it off yesterday. I don't think I have that many. So let's just try this one. We'll go till the bell rings. A standard poker hand consists of 5 cards dealt from a deck of 52. Do you guys know cards?
Yes.
Do you know there's 52 cards, 4 suits, 13 suits? No? Okay, so Sam, on those, we're have to. Most of the time, it will tell you, but it's surprising how many people don't know cards anymore. So, how many different poker hands are possible? So, does the order matter in a poker hand? No. Like when I arrange it, it does, but in general, it doesn't matter, does it? Okay, so how many? What choose what?
And
52.
So 52, choose 5.
Choose 5. So 52 factorial over 52, 12, 47 factorial? Over 5 factorial? Now, you think, oh my gosh, there's so many numbers. But I really only need to write 52, 51, 50, 49, and 48, don't I? Over 5, 4, 3, 2. So that gives me 10. That gives me 12. I don't need to because at the 47 factorial reduced it all. 3 goes into 51. 17. And 2 goes into 12. 6. So I have 52 times 17 times 10 times 49 times 6. Is it appropriate to use a calculator?
Yeah.
Yes. 52 plus 17 plus 10 plus 49. No, thank you. 52 times 17 times 10 times 49 times 6. So, there's only a few. 2, 5, 9, 8, 9, 6, 0. So there's only 2,598,960 different poker hands that you could have. So